Okay, I'd like to introduce our first presenter of the capacity testing, PV capacity testing section of the workshop. Jim Crimmins, CEO of CFV Labs, will be discussing PV plant underperformance from a lab, field, and modeling perspective. Here you go, Jim.
Thanks, Ann. You here? Okay, as Ann mentioned, Jim Crimmins, I'm the CEO of CFV Labs. Some of you guys probably know us. For those who don't, we are a third-party test lab and research lab in Albuquerque, New Mexico. There's a couple of pictures of our facility. We've been involved in PVPMC as a co-sponsor since 2018. It's one of our favorite, if not our favorite, workshop conference, as I know some of you guys feel as well. We held 3 of these in Albuquerque a while back before COVID. And so we know quite well the amount of work that goes into putting on one of these. And we'd just like to thank Groundwork, Cameron and Ann, and the rest of the team for what they're doing. It's a lot of work, and they're doing a fantastic job. Okay. So today's topic is PV power plant underperformance. There's a lot of good news in the solar arena these days, whether it's the IRA package of incentives and so forth, onshoring, just general overall growth. But one problem that seems to still be top of mind, or at least top of mind in the press, is this idea of underperforming PV assets. Okay, so this is just a snapshot, from the trades. You guys all know this. You can any week wake up and see stuff like this. Solar assets are underperforming. Underperformance is costing us a lot of money. Shortfalls, chronically underperforming, lots of phrases like that. The bottom one is my favorite: underperforming solar assets shade the entire industry. So one thing we should ask, I think, is should we be skeptical of these underperformance claims? So I can make the case both ways to the group here. So one, on the yes side, yes, you should be skeptical, is that press outlets like provocative stories, right? And these are kind of provocative headlines. The bias is generally toward negative news rather than positive news when you're trying to generate provocative press. And some organizations may have interest in making these claims. On the other side, no, we should not be skeptical. It's true. I think the fundamental reason, as we see it, is that PV power plants are very complicated things, right? Lots of things can go wrong. There are way more wrong ways to do things than right ways to do things. And especially in times of extreme cost pressure, and high supply chain and technology volatility, it's not ultra surprising that we have some underperforming assets. We've also got some data from some pretty credible sources. That's a bar chart, I believe, from DNV that I took out of an NREL paper, so that's now third hand. If anyone from DNV thinks I'm misrepresented it, let me know. But they did a study, I think, about 40 assets and had sort of a median underperformance of around 3%. So I think, on average, I'm going to come down on the side that there is some truth to these claims, whether or not it's sort of overrepresented in the press. Some other evidence for you. This is experience from our test lab. So we're getting, way more incoming power plant performance analysis requests than we used to. If you look at the timeline there from 2014, when I started working at CFV to now, that graph represents the percentage of power plant related projects at CFV. So it went from maybe 5% in 2014 to maybe 60% or 2/3 right now. Again, that's not surprising given the fact that the installed base is, way bigger. And also when the ownership of CFV changed in 2020, we probably have a more of an interest in power plant kind of related issues. But I would say that it's kind of interesting to look at the kinds of issues that we have seen in the past and the issues that we see now. So in 2014, a big thing was snail trails. Some of you guys who have been in the business for a while will remember that. That kind of faded away in 2018. Cell cracking has been a popular favorite topic forever, and it continues to be. Backsheet cracking from some of the older, backsheet like AAA that were used in the past. Module degradation. But some more recent things and some things that I think they're maybe responsible for some of this increase in incoming into the lab for requests for testing and analysis are severe weather event failures. So I think that some of the mechanical properties of modules have changed quite a bit in the last 4 years. That is one of the drivers of that. And something that's really new, at least for us, is incoming requests to help work on capacity testing failures. Okay, so power plants that are new, they're being built, and they're not able to pass their capacity testing requirements. And those are pretty stressful calls usually coming in because the time pressure is so intense. So this is another thing that gives us some kind of, I think, even if it's just empirical or anecdotal, evidence that this underperformance issue is potentially real. So what's going on? So first, I think what we want to do is define what underperformance means. Maybe that's obvious to a lot of us. But one thing to understand is that underperformance is always and everywhere relative, right? It's underperforming compared to something. And what it usually is a model. And so this group is, well equipped to understand this idea. So we're taking some power plant measurements. Typically they're A-side meter measurements. Sometimes they're DC side. The actual components in the field are operating as the actual components in the field operate. And the weather data, so to speak, in terms of measured performance is real-time data. It's the actual weather in the power plant. Now that is being compared to some kind of a model, and there's different types of models that are used for different types of purposes. So for a lot of the time, we're talking about energy yield models here. So things like PVSys, SAM, Plant Predict, Solar Farmer, and so forth. But sometimes, for example, in the case of capacity testing, we're talking about standards that have sort of embedded, let's say, regression type models in them, like ASTM 2848 or IEC 61724. Into those models, at least the energy yield models, go representations of the components that are going to be used in the simulation, the model simulation, including pan files, inverter files, tracker parameters, on and on and on. So those are sort of the assumptions, or sort of parameters that go into the model. And then there's weather data. And as we heard sort of in the first session, there's different kinds of weather data. There's real-time on-site data, there's satellite data, there's TMY data, long-term historical resource data, et cetera. So when we're talking about underperformance, it's definitely an A-B problem. The more optimistic, let's say, the model is, the harder it is to, not have underperformance. And the more poorly the components or the construction of the power plant behave, the more difficult it is to not have underperformance as well. So what's going on? So one thing I want to do in the beginning here is kind of carve out this long-term solar resource estimation as maybe a separate issue from, sort of something like capacity testing, where you've got a model and you're looking at the real-time weather data, on site, right? So I think some of the things that people think about in terms of underperformance are related to this, maybe overestimates of it and so forth. I am no expert in that, although there are some here today. So this is a different issue. That graph kind of shows you how long it takes to kind of stabilize an estimate of what your long-term, solar resource is. And, you can't take 2 or 3 years of underperformance and sort of claim that, you're out of the game of the original estimates, right? It takes like 10, 15, 20 years. So that's a different category, I think, of underperformance. So let's go back to the energy yield models, which is more like what's being used, in the case of power plants, capacity testing, and things like that. So it's possible that some energy model inputs into PVSys or SAM or Plant Predict or something, are overestimating performance. One thing that we're pretty familiar with are pan files, which is a big driver of the energy yield estimates coming out of these things. And we still see people using manufacturer generated pan files. They are definitely, I can tell you this, are not as reliable as third-party lab generated pan files. Manufacturers may supply you with third-party pan files if they have them, but sometimes they don't, and they generate their own. So developers should be more invested. I think the original text there was way more invested in generating their own pan files from modules sampled from the project supply. It's not that expensive, and I think that's something more people should be doing. A second kind of issue is the IAM profile that goes into pan files. This is a little bit of inside baseball, potentially. But that basically, for people who are not familiar, describes the response of the module or efficiency of the module in generating power as it's tilted off axis from the sun. There have been a number of instances of pretty, let's say, dubious IAM profiles being generated and stuck into pan files, even quite recently. And that's something you need to watch out for. The IAM measurement is very difficult. We do this outdoors at CFV. Other labs do it indoors, but it's just a tough thing to measure. In effect, with the kind of coatings that are being used in PV modules, which are very simple, sort of single layer thick film coatings, the actual IAM profile is almost always going to resemble some kind of default Fresnel equation, which is a very simple equation involving the indices of refraction. And therefore is going to be, very similar to something like the PV-Syst default ARC IAM profile. So that graph on the right shows a green line, a green dotted line, which is the PV-Syst, I think, non-ARC default setting, a dotted blue line, which is the PV-Syst default ARC IAM profile. Some measurements we took at the lab, which are right on top of that PV-Syst ARC coding line. And then the red line is made up, but it's like we've seen stuff like this, right? Stuff that's just way, way far away from something plausible for the type of coatings that are being used in PV systems these days. Here's another one that's kind of a popular topic. There's going to be some posters on it. There's some thinking that models that are using hourly data may be overestimating performance, especially in areas with high let's say sub-hourly irradiance variance due to clipping and how the models account for the clipping and kind of miss some of the sub-hourly clipping when there's a lot of variable irradiance. This is also especially important for plants with high DC-AC ratios. So the order of magnitude of this effect seems to be on the order of maybe 0 to 3%, depending on site parameters and the variability of the sub-hourly irradiance. This is big if true. I think there's a consensus that it probably is true to some extent. There are some validation exercises underway, with some of the models and so forth. But I think this is something to keep an eye on, and people will probably start adjusting, model outputs for especially areas with high sub-hourly irradiance variance. Okay, here's another thing, soiling. So soiling losses for projects that we're working on, we'll ask folks like, okay, your power plant is underperforming, what about soiling? And we'll typically hear, oh, it's not a big deal. We cleaned the modules last year, things like that. So the soiling losses may be much, much larger than reported visual estimates from the field. People you're talking to may have never even been to the power plant, and also may be larger than model estimates. Even for newly built plants, you can have soiling events that come up very quickly in certain parts of the country and disappear very quickly, as opposed to sort of the gradual buildup soiling that I think most people think of. Soiling can be highly variable across a power plant. Multiple soiling stations are needed. We're working on a power plant right now that has, I think, maybe 30 soiling stations being installed, something like that. It's important to calibrate the soiling stations accurately. And there's also some new innovations are coming out with combinations of soiling measurements and sort of in situ module performance degradation ideas, which I think will be quite interesting. Okay, what's going on? Modules performing below nameplate. This is right in our wheelhouse. It's very difficult to diagnose module degradation or underperformance from operating plant data, right? So you've got issues like clipping, curtailment, amongst others, variable weather conditions, temperature variations, all kinds of stuff. And although on-site soiling is another example, although on-site string testing is possible, we do it in certain cases. Lab flash testing is really the best option to accurately determine module health. So surprisingly, we still see pretty large projects that do not have independent flash data, either in the module QA process or, around commissioning or at any time at all. So probably this is a confounding variable, but a large fraction of the plant underperformance projects we are involved in will have module slash maybe 3 or 4% under nameplate after less than 6 months in the field. So they're definitely underperforming module LID estimates, especially with some of the new LID assumptions for new doping techniques and so forth. So, this big takeaway here is it's not that expensive to flash some modules as part of a QA process or as part of an EPC process, and people should be doing more of it. I think it's much more difficult to sample them from the field later. Okay, some other miscellaneous issues that we are seeing on projects we're working on. Uneven terrain leading to tracker module shading and underperformance. I'm going to note that these are usually older tracker designs. Newer designs have both hardware and software means to mitigate this problem, but some older installs on uneven terrain may need updating, for example, software that can kind of at least try to minimize that problem. Ground faults due to connectors, connector mating, or other kind of wiring failures and things like that. Surprisingly common, and can be, some of these issues are larger performance problems than you might think, if they are significant enough to trip breakers, right, or trip inverter shutdowns and things like that. Mentioned before, module breakage and extreme weather events. Weaker module frames and glass are leading to increased glass breakage rates in the field, sometimes complete module collapse. Again, it may not itself sound like a big issue if, 0.1% of your modules crack. But if they trigger inverter shutdowns or other kinds of safety problems, it could be a bigger problem than you think. Okay, so when we get involved in a project, first of all, there's a lot of people involved in these projects besides CFV labs or another test lab, right? It's a very multidisciplinary kind of attack on the underperformance problem. So here are some typical steps that are taken. We'll go through them a little bit, and then we'll talk about some of the stuff that we do that we're more, familiar with and heavily involved in. So usually there'll be a performance data review, which is triggering the idea that there is underperformance and, that maybe capacity testing isn't going to work out, for example. Or if it's a power plant that's been operating longer, they just may have a suspicion that it's not performing up to par. And that could be internal, it could be external. There's a lot of good consultants who can do that kind of work. In a newer plant, there'll be a model parameter review. So for example, the owner may own the energy model and the EPC may take a look at the PV sys parameters and say, hey, some of this is unrealistic. There may be a scrub down of the pan files if they're manufacturer supplied, and things like that. In some cases, there'll be a thermographic flyover, either as part of an as-built kind of idea or as part of a diagnostic operation. Sometimes field EL is done, sometimes field IV curves. There'll be some MET station checks to see if the MET station is operating correctly. Although that usually leads to an overperformance problem for things like dirty sensors, right? There'll be an attempt to do soiling checks. I think there should be more of that. Visual sort of soiling checks are not always that productive. And some of that may come back to our lab actually for estimates of soiling, which in the case of some kinds of modules and module, cell or absorber colors can be very difficult to see visually. In red there is module performance checks in the lab. That's something we'll talk a little bit more about in a minute, and that's something we're very heavily involved in. And again, there's more stuff going on. There's ground fault and connector checks, inverter availability and performance checks, tracker availability and performance checks, all kinds of stuff. So we'll talk a little bit more about what we do for module performance testing in the lab. So here's what we recommend for folks who want to take a look at how the modules are doing in their power plant. Again, this is going to be like a compared to what kind of exercise, right? Compared to nameplate is one idea. but there may be some existing flash test and EL data from the manufacturer or potentially other third parties or PAN files or something like that. So it's good idea to grab that, make sure it's available. Get all the serial numbers, module model numbers, bills of material if you can get that data about the modules, date of manufacture, date of installation. Grab all that information if you can. Gather plant performance data, thermographic or other field data, and potentially try to identify locations in the plant of particular concern. So it's usually the case that there are certain quadrants or sectors or areas of the plant that are performing worse than others for various reasons. Sometimes that's soiling, sometimes it's a different module type, sometimes it's inverter reasons. But you want to kind of target, you want to find the stuff that you want to maybe oversample if it's performing poorly. And then, you want to develop a sort of a coherent sampling plan of the modules, which will stand up to scrutiny if other parties are going to kind of look at it. So develop a sampling plan based on identification of potentially independent populations, and we'll talk about that in a second. And then you send the sample modules to the lab for visual inspection, EL imaging, and flash testing. All right, so a question we get all the time is power plants are big. We've got hundreds of thousands of modules in these power plants, maybe millions in some cases now in different parts of different power plant projects. So how many do you need to test? So the first question, or the first thing you need to understand is that if it's an independent uniform distribution, and it has sort of this Gaussian shape that you're familiar with, you don't really have to sample that many modules to get a good estimate of the mean power output, okay? If you're interested in the tails of the distribution, if you're interested in like 0.1% defects, then you have to sample a whole bunch of modules. But if you're interested in just getting a read on the mean power, 20, 30, 40 modules is plenty, okay? And so that's like one insight. Now, it doesn't apply if the distribution isn't normal, and it doesn't apply basically if you have a big power plant and you have more than one, basically populations of modules. And I think that's actually the key point here. Here's the error of the estimate of the mean for normal distribution. Drops very quickly with the sample size 1/(n). Note that this error really doesn't depend that much on the population project size at all. Actually, it's kind of independent of that, which is kind of an interesting statistical fact. So as I mentioned, you only maybe need 20 to 40 modules. So to give you a sort of something to look at in terms of what that means in terms of watts, or, on a module or something like that, and what the sampling error would be for a normal distribution. At 20, you're sub 1%, 40.6, 80.4, 160.3. There's sort of diminishing returns there. You can compare that usefully to flash testing errors for PV modules in a flash testing program like ours, which is around 2%. So at some point that error is bigger than the sampling error by a lot. And so you can see that you don't need to be really sampling hundreds of modules. Okay, so the bigger issue, I think, if we look at a large PV power plant like this one in China, you can see that, the idea that there are maybe multiple populations of things that are different from each other is not difficult to see. And, so certainly geographically, those different patches may have, different soiling, wind, temperature, all kinds of stuff. When we're working on plants, we want to know everything about the population of modules in the plant. And so some things that we have cross-sampled are things like module manufacturer. Some big power plants have more than one module manufacturer. Certainly module models may be different. Module bills of materials we are very concerned about, especially if it's cell type or cell manufacturer. Module factory. Most of our very large manufacturers now, or all of them, have 3, 4, 5, 6 factories that modules can come from. For a big build out like this, these modules probably came from a couple of different factories. So that's a different population. Module production dates. Manufacturers have different kinds of processes in place to sort of track different production variables and things like that for module production dates. And that's, again, there are better and worse modules that come off lines at certain times. And as I mentioned, location in the field. So that just gives you, sort of a snapshot of kind of the degree of specificity that you'd like to attack this problem with a large power plant. And again, this is one part of a very multidisciplinary kind of exercise to try to look at why these things might be underperforming. This is just sort of the lab aspect of it. Okay, so briefly, some conclusions and recommendations. PV power plant underperformance is a highly multidisciplinary topic. We have the Zoom calls to prove it, right? So if you're involved in one of these projects, you may have a highly multi-partite Zoom call quite frequently. Because performance is measured against models, it is important to examine both sides of that difference equation, A minus B. Many factors can affect both model output and performance in the field. It's unclear and probably unlikely that plant performance data alone can identify all issues very easily for reasons I've mentioned. If you are going to embark on one of these exercises, you want to develop a structured plan for lab and field testing if appropriate. Even if time is short, even if you're up against your capacity testing deadline, it makes sense to take a pause and think about what your strategy is. And then I think bringing the performance analysis groups, say within a developer, together with the field and lab testing folks sooner rather than later, tends to usually make things go a little bit better. And that's it.
Thank you, Jim. Next, we have Ben Taylor from Taylor Data Consulting. He's going to be speaking on PVCA